parameter depends on? It depends on. So it's simply y times the a1, a2, and plus I, the permutation. That's it. So this is, if you want, you can also rewrite it, imagining that there's a auxiliary operator. So for this we deduce R AB lambda is actually L AB lambda plus I equal to 2. Okay. So that's basically, so now if we can do a graphical representation of this commutation relation. Basically, if we represent, so each of those starting point as a kind of vector space. So if you want, this is your auxiliary vector space V1, and this is your physical Hilbert space Hn. There will be some states associated with each of those vector space, and then they interact through the lax operators, or equivalently the R matrix. So we'll be denoting this guy as NA1 because we have V1 here, and of course this is equal to R N A1 lambda minus I over 2. Okay. And then this relation can actually be represented by the following diagram. See if I can draw this correctly. And with a label V1, A2, N, and then this guy will be R1, 2, and this will be R, N, 2, and this will be R, N1, and whereas here will be again A1, A2, and this will be R, N1, R1, 2, and R. So each of those vertex, basically, in time, goes this way. So basically this is telling you, so the ordering, so each of those guys is basically Rn A1 lambda minus I over 2, and this will be something like R and A2 mu minus I over 2. So you can also rewrite it, those guys in terms of the R's. But the ordering in this communication relation matters. And they can be indicating by, if you're reading from left to right, that how those matrices are kind of multiplied together. So the first one is basically what you have in the left-hand side, that sort of two auxiliary space A1 and A2 whatever states, they come in and they interact through this R matrices R1, 2, and then next you act on you basically interact again at this vertexes via the R. Wait, did I get the order wrong? Oh yeah, because I can't draw a diagram properly. So. Yeah, this is sorry. So the time, so the next one, then you interact. So basically, as your time go, as you read from left to right or along the time evolution, then interact again between the state n and the state A1 via this R matrix Rn1, and then finally the state n talks to the states in the vector space V2 via this R matrix Rn2. But this has to be equal to, if you interchange the order from basically the interaction order by moving, let's see if I can get it. Right, by moving this line, instead of going this way, but now you actually talk to it. So instead of here, you move to the left. So that's right. So something like this. So this would be Rn1, and this would be Rn2, and this would be n. So this has to be the same as if you move this n state towards the, so basically before, I guess the best way to say it is actually before A1 and N2 exchange. Basically, if you want, yeah, okay, here is a punchline. The best way to say it is actually that how each auxiliary space exchange with your physical space n should be independent whether you exchange the auxiliary space first or exchange the auxiliary space after the kind of physical exchange. So it doesn't matter like which way, it doesn't matter like if you have a line this way or kind of before, this will be after the exchange, and the exchange before the exchange in the auxiliary space, which occurs right here. And that's represented by this matrix here. So if you want, you can read it out from the left to right. You first have R and 2, so this will be this guy. And this will be R and 1. Next takes place, and finally here. So this is actually, this diagram is a famous kind of representation of the so-called Young-Baxter relation. Okay, so, and in fact it occurs in all sorts of contexts. For example, if you look at the scattering process in 2 dimensions, this will tell you that so what usually occurs is that for each of those incoming lines, there will be some particle with some given momentum states. So those momentum will be labeled, in fact, by those spectral parameter lambda and mu's. And each of those so-called R matrices actually representing a scattering process take place for all these kind of external particles. And basically this diagram is telling you that even though if you have now kind of 3-body scattering, it doesn't matter. So you can actually factorize this scattering process into pairwise scattering. So each take place at those vertices here. And it doesn't matter which order, well, it doesn't matter of which order you are actually placing, say, one of them, well, this line here. So I'll give a more kind of explicit illustration later. But as an immediate consequence, so let's see. Well, I think now is a good place to stop for like